large granite sphere is an interactive sculpture that is at St. Rita's Medical Center in Lima, Ohio. I think these are made by a company in Finland, and they're found in other metropolitan areas. I guess there's a larger one at Easton Mall in Columbus, Ohio. So the lab is to determine the mass of this sphere. When I saw this for the very first time, I thought, gee, I wonder how much that weighs. And I've done this experiment a few times. I've been there when people walked up and said the very same thing. So it's kind of a natural question. And when I thought that thought, I said to myself, well, you know, I'm a physics teacher. I can figure out how much that thing weighs. So came up with a lab to do it. And you can do that lab with us too. We'll be your silent partners, literally and figuratively here, and collect the data. You can get it right off the screen remotely and do this lab right in your classroom anywhere in the world. This lab is organized in this following fashion. It's determining the mass of a large granite sphere in an interactive sculpture. Chapter 1 is collecting the data, so we've made video of this, and it's just as if you're there looking at the data with us, and you can collect the data remotely this way. Chapter 2 is performing the calculations, and this is chapters 1 and 2 are pretty much at the high school physics level. I'll go through the steps of how to do the calculations, and what substitutions to make, and how to come up with the equations. Chapters 3 and 4 are beyond high school physics level, possibly AP Physics, but these are going to be at for a calculus course, or an AP Calculus course, a college calculus course, or AP Physics course, or college calculus course, and showing how do you come up with the integrations to get the equations that we use. So this is explained in part 2 of the video. It's a second 15-minute or so segment. After I'm done with chapters 1 and 2 here today, we'll skip, if we've got time, to chapter 5 on instructor hints and tips. So you obviously can't hear this. I've done this lab before with instructors, and the audio came through because we're used to hollering, but students are like, oh! I discovered for the first time doing this that you can't get audio with students, so we really needed to mic them up, and we're not going to redo this. But what she's saying is basically that we're going to determine the mass of this sphere, and we're going to use a ribbon to spin it, and a spring scale, and a stopwatch, things that we could all get in our school easily, and except we're using a phone now instead of a stopwatch, and spin this sphere up. And the bigger this sphere is, and especially the heavier it is, the more slowly it will spin up. So we can come up with an equation to measure that mass that way, or to determine the mass of it that way. And here they go. From rest, pull it with a ribbon at the circumference, and it slowly accelerates, and we let it do one full rotation. I've got that marked with a little piece of paper there. And there we go. That's the end of that. So that's your data collection. That's what it looks like if you were here doing it with a team of students. In order to do the calculations, we measured time, the ribbon circumference around the sphere as it spun out, and if you have the opportunity to do this lab with a similar sculpture somewhere, use ribbon. String, you'll have a terrible time getting it to stay on. We came across ribbon by accident by forgetting the string or getting a string that was too short. Ribbon works much better. So time, the ribbon circumference with the sphere circumference as measured with a ribbon, and the force applied with a spring scale. That's a little tricky, but we'll talk our way through that. An attempt was made to maintain the force at 16 newtons. If you're pulling with that spring scale, and you'll see them doing here, and trying to maintain 16 newtons, you'll be a little over, a little under, a little over, a little under, and it'll wobble around. But that great big heavy sphere has so much inertia that it all kind of averages out, and you can get really, really good results. So I think we came within about 1.5% this time for error. On the following pages here, you can go ahead and collect the data for yourself and do the lab in your classroom. So here's the data. It's trying to maintain 16 newtons down here. That's what it would look like to the student collecting the data. We'll call it 16.0 newtons. Probably some error there. But we'll do the best we can. Our method of applying the force is crude, but with practice, after 2 or 3 trials, you can get decent results. You could, I suppose, rig up a system of pulleys with a falling weight. That would give you a little better results, but this works just fine with some practice. So we're going to show you the time and distance measurements and how we got that.
The circumference of the sphere was determined to be 2.84 meters.
2.84 meters. You were able to pick up a little audio there. So you just lay this ribbon out. I marked it with a marker and lay it out on a tape measure and get the measurement that way.
For trial 4, the time was 12.10.
Okay, 12.10 seconds for one of our trials. That day we did 3 or 4 or 5 trials and averaged the results. This data that we used here is for one of the trials that we did. It came out really close. So now take the measurements that we just did on the previous screen, calculate the mass of the granite sphere yourself. The time was 12.10 seconds, the circumference is 2.84 meters, and the force is 16 newtons. So how to do the computation continues with Chapter 2 right now. If you're attempting to do your calculations here, you may want to pause while your students do the calculations or come up with the equations. So if they don't need much guidance, maybe you can set them loose on this project at this point. While you're waiting here, this experimental video was performed by Ottoville class of 2017 physics students, all seniors, 7 of them. If you have questions about the lab, you can contact me. I'm Kevin Blake at my email here, kblake@ottovilleschools.org. Okay, we'll go into Chapter 2, so if you don't know how to do this, I'll walk you through it. So in Chapter 2, we are using the equation torque equals moment of inertia times angular acceleration. Tau equals I times alpha. Maybe that's iota, not real sure. To do the calculation, we can arrive at this equation experimentally. That's one way to do it. But let's back up to something your students would be familiar with at this point. For a linear system with acceleration, we have the kinematic equations. You could have S here instead of X, depending on your publisher, on your book. But displacement that you end at is equal to the original displacement plus original velocity times t plus 1/2 times a times t squared. And Newton's second law, force equals mass times acceleration. By the way, if you contact me, I've got a video that explains how we get this, if you don't like it falling out of the sky. There are analogous kinematic equations for systems undergoing angular acceleration. In this case of the lab, a sphere starting at rest and rotating faster. So these two equations that you're familiar with for something moving in line has equations very much like it for things spinning. So the angle theta that an object ends at is equal to its original angle theta plus its angular velocity originally times t plus 1/2 its angular acceleration times t squared, and torque equals I alpha is analogous to F equals ma. Torque is equal to moment of inertia times angular acceleration. Okay, so this granite sphere started from rest. Got a good shot of that in the video. So for later use, we can eliminate most of the terms for one of the equations. Even though this is spinning, the ribbon coming out from the sphere was moving in a linear fashion. So we can use these linear equations that we're used to because they describe the ribbon's motion. The displacement that the ribbon ends at is equal to the original displacement, which was rest at the starting spot, so we call that 0. Original velocity, it was at rest, so we call that 0 times t, so these two terms are 0. And we are left with 1/2 at squared. So under those conditions, x equals 1/2 at squared. And notice that I've written this in burgundy because I'm going to use it in a substitution later. And I like to color code when I use substitutions. So we'll come back to this. Don't forget it's there. Okay, we can make many substitutions into this equation. Torque is equal to moment of inertia times alpha. Well, first of all, torque is force times radius. We don't have a torque wrench to do this lab or a torque meter of any kind, but we do have a spring scale that measures force, and we could come up with radius based on the circumference that we measured with the ribbon. So if I substitute force times radius in, we're starting to get towards some measurable quantities here, equals I times alpha. Now, for a solid sphere of uniform density, moment of inertia, I, equals 2/5 mr squared. Now, for some of you, well, that equation, maybe we get it experimentally, maybe it falls out of the sky, somebody made it up and it works, but there really is a way to come up with this. So in chapters 3 and 4, where I show how the calculus is done, refer to chapter 3 to see how I came up with this equation. So at the college or calculus level, maybe you can look at those and see where that comes from. At the high school level, we'll just substitute those in there, but there's a way they come up with those. Okay, the next thing is we've got this angular acceleration alpha, and we've got no meter to measure angular acceleration. So what we have to do, you may be familiar with at the high school level, x, displacement, equals r times theta, and v, velocity, equals r times omega. And what I've got here, a, acceleration linearly, is equal to r times alpha. Well, I don't have this alpha, but if I put in a over r for alpha and make that substitution, now I've got stuff that we can measure. We can measure r from circumference. We're looking for m. We can measure force. We got to do something yet with this a, but hang on. You might see where we're going with this. Okay. So let's take this equation where we're at so far on to the next page. And since on this object we are spherical uniform density object, we are adding this force at the outside edge of the sphere. The little r and the big R are the same r. So they do cancel, and this is often the case when you're spinning an object. This is not always the case, so you have to be careful, but it is often the case, and it is the case this time. So the little r and the big R are the same r, so this one, let's say, cancels with that one. This one cancels with that one. And we're down to F is equal to 2/5 m times a. Now, earlier, we made that substitution for a sphere starting from rest, and in Burgundy, we come up with x equals 1/2 at squared. If I shuffle that around and solve for a, I've got 2x over t squared. Now we've got, and to make that substitution, we've got everything we can measure. We're looking for mass. We've got a spring scale to measure force. We've got an x to measure the ribbon distance. We've got a stopwatch we can measure t, or at least a phone we use for a stopwatch function app. Rearrange this equation to solve for mass, and m equals 5 force times t squared divided by x. Using our data again, if we put in the 16 newtons and the 12.10 seconds, square that, and the 2.84 meters for the distance from the lab screenshots that you had, and we come up with the mass of the sphere being 1,031 kilograms. If you use gravity at 9.8 meters per second squared, there are 2.20 pounds in 1 kilogram. Make sure you've got your gravity at 9.8 because that's the only time this works. Multiply that out, and it comes out to 2,270 pounds, which is 30 pounds away from the shipping weight, 2,300 pounds. So that's very close. It's a little over 1% error, I think. That sphere is on that rubber base, and they pump water up underneath of it. It's very low friction. If it's at rest, it takes very little force to get that twisting and moving, as heavy as that huge thing is. Okay, so if you are working at a higher level, college level, calculus level, AP Physics or something like that, you may want to go into chapters 3 and 4 on the other video. I think it's part 2. And we show how to do all of these calculations here. But I want to skip back to, this is kind of what it looks like. I want to skip back to chapter 5 for the hints and tips. Okay, make sure you use a ribbon instead of a string. There's a story behind that, but we stumbled onto that one by serendipity. Disc and disc are both spellings, as far as I can tell, are okay. Notice that granite is a rock, and rocks are composed of minerals, and the composition of that can vary somewhat. So that makes granite a heterogeneous mixture technically. It's not a truly precise uniform density.